All right. So, happy Friday. Hope you're all doing well. Hope you're all staying healthy, and hope you are all working on your assignments. The Chapter 5 and 6 assignments were due yesterday. And good morning, good morning. The Chapter 7 assignments are currently due this coming Tuesday. We're also, again, on track to resume our normal next week, so be aware of that. If you can't make it in for any reason, that's fine. I'll still be recording the lectures and posting them for you, but the option will resume next week. We're finishing Chapter 7 today. There's just one formula. We're going to mostly talk about some concepts, but we're also going to go into depth about the formula that I introduced yesterday, the specific heat formula. And that will close out Chapter 7, so you'll have everything you need to do that homework. Next week, we will pick right back up with Chapter 8, which takes the Chapter 7 information and applies it to some additional topics, including pressure. So we're going to tie the last couple of weeks in together next time. As an additional reminder, be aware that the next test is on the horizon. I predict it being about 2 weeks from now. So next week we'll cover Chapter 8. Week after that we will review, and the test will be made available to you. Any questions about any assignments, announcements, scheduling, any material at all before we continue today? Okay. All right. So if you have any questions about any assignment at any time, please cut me off, interrupt me however you can. And so let's resume discussing specific heat. Turn with me to slide 17 of the Chapter 7 notes. That's the slide that I am showing right now. We were discussing specific heat and what this physically means and what this formula means and how to use it. So we've been talking about thermal energy and thermal energy transfer. As thermal energy enters or exits an object, there's going to be when thermal energy enters an object, you're going to increase its temperature. When you take thermal energy away from an object, you're going to decrease its temperature. That is what this formula here represents. The Q represents the heat added to or taken away from the object in question. If you add a positive amount of heat to the system, then temperature will rise. You'd end up with a positive delta T over here. So positive heat increase, positive temperature increase. Meanwhile, if you take thermal energy away, Q would be a negative number. The object now has less thermal energy. A negative Q over here would mean a negative delta T. Means your temperature would drop. Remember that this is delta T. This is the change in temperature. So all this tells you is for a specific object, removing or adding a specific amount of heat will change temperature by a specific amount. Now, you can add the same amount of thermal energy to two different objects. This takes that into account. Sorry, I heard someone's mic turn on, so I immediately thought, question? Anytime I hear anything, I think I'm probably going to instinctively pause. So this formula has two terms in it that take into account the specific object that you are adding thermal energy to. The first is the mass term. When you add thermal energy to an object, its temperature will increase depending on the mass of the object. The more mass an object has, the more thermal energy it needs to change its temperature by the same amount. If something has 100 times more mass, it'll use more thermal energy to increase its temperature the same way. When you're boiling water to, say, make noodles, I use that example a lot. I eat a lot of noodles. It takes longer to boil a larger amount of water. You have more mass, so it needs more thermal energy. to increase its temperature by the same amount. Less mass means the object will heat up faster. The other part of this formula that talks about the specific object involved in the question is C. C is a new variable. This green marker is dead. Red's visible. C is specific heat. And this is a variable that describes how much thermal energy a specific substance needs in order to change its temperature. Every substance has a different specific heat. I want you to cast your mind back to a time where perhaps it was summer and you were going to the lake, to a pool, to the ocean, probably going on some summer activity involving a body of water. Now, if you were a kid like me, or still an adult like me, you arrive at your destination, you're going to get in the water anyway, so you get out of the car without your shoes on, because you're just going to have to take them off later anyway. You leave your shoes in the car, you get out, and you step your feet down onto the hot, hot concrete. It hurts. It's not fun. So your first instinct is probably to get off of the concrete and get onto some other surface. So you leap over and you land on the grass. Now, the grass does not feel as hot. The grass does not burn your feet like the concrete does. But why does it not burn your feet the same way the concrete does? The concrete and the grass, so concrete slab, grass next to it, they're touching one another, like they're connected through the earth, so they should be attempting to reach thermal equilibrium. They should try to be at the same temperature. They're also both getting the same amount of radiation from the sun, and they're both touching the same temperature air. So why is the concrete and the grass different temperatures when everything going on around them says they should be at the same temperature? The reason is because of specific heat. Different types of materials need different amounts of thermal energy to change their temperatures. There is a specific table, a chart on slide 17. And I want you to pay close attention mostly to the first column, which lists the type of substance being examined, and the second column, which lists the specific heat in terms of joules per kilogram per degree Celsius. Now, materials that heat up very quickly, things like iron, lead, silver, tin, mostly the metal elements on this table, those types of materials have very low specific heats. That means they don't need a lot of thermal energy to increase their temperature very quickly. And most concrete, most stone is made of metallic compounds. So rocks and concrete contain metal in them. It's usually in a combined molecular form, but it's still metal atoms. And so concrete will still have a similar specific heat to the metals that it's made of, which means it's going to have a very low specific heat, which means it's going to heat up and change temperature very, very quickly. Conversely, the thing on this chart with the highest specific heat, if you look at the bottom, is water. Water has an incredibly high specific heat, whereas a lot of the elements on this table have a specific heat of like 100 or maybe 700. Water's specific heat is over 4,000 joules per kilogram degree Celsius. It takes an extreme amount of energy to change the temperature of water by even a little bit. And grass is mostly made of water. Grass, plants, the water itself, at whatever body of water you were going to in this summer example, it takes a lot of energy from anything, including the sun, to make that particular type of, to make water specifically warmer. So they are touching, they're trying to reach thermal equilibrium, but the temperature of the concrete has just increased so much faster than the grass that you notice that difference. So this is all due to specific heat of different materials. Another example of this, still a summer sort of example, say you get back into your car after it's been sitting in the sun for a while. You get in, you're able to sit pretty comfortably on the seat and touch the dashboard and the steering wheel. They're warm, but they're not unbearably warm. But then you reach to fasten your seatbelt and your hand touches the metal of the seatbelt clip. And that part, the metal part, is what burns you. Because again, metal is going to naturally heat up more quickly. Even when exposed to the same amount of thermal energy, it's just going to increase its temperature faster. This principle, specifically the fact that water's specific heat is so incredibly high, is one of the things that makes life possible on planet Earth. Frankly, a lot of the reason why Earth is habitable is because it's covered in water, and because water has a lot of very specifically unique behaviors. For this specific example, because water has such a high specific heat, it takes a lot of thermal energy to increase the temperature of the water, and that's why during summer, if you jump in the water, it's still cold. Even in the heat of summer, the water is not absorbing enough thermal energy to increase its temperature very much. And this, conveniently, is one reason why the sun does not boil our oceans. If water had a specific heat more like iron, more like mercury, then the oceans would probably boil from the heat of the sun, which means everything living in the ocean would die, and our atmosphere would be full of hot steam all the time, and there'd probably be no liquid water on the surface of Earth, thus making the planet uninhabitable. Earth was very specific to us, intentionally so. So that is the ins and outs of this formula. We're now going to use this formula in an example. If you move on with me to the next slide, this is slide 18. We're going to use this in a very specific example. And I do need to go ahead and apologize, because when I was writing this example, and I didn't realize this before I sent the notes out. I want to address it now because the copy you have is slightly out of date. I left a variable out of this specific example. So as we're reading it together, I'm going to make it. So this specific example involves the work of a metallurgist. That is the scientific name for a person who studies metal and their behaviors. Metallurgists very often use this formula in an attempt to identify certain materials. Because if you know the mass of something, how much thermal energy you add to it, and how much its temperature changes, then you can estimate its specific heat, and then you can look at our handy-dandy specific heat table to figure out what it's made of. So there are scientists who use this method almost exclusively to figure out what something is made of. It's useful for that reason. So in this specific case, a metallurgist is heating up a sample that has a mass of 100 grams. This metal is grayish, and the variable that I left out is actually what the material is made of. So I'm going to go ahead and tell you guys, we're going to assume that the metal in this example is silver. It's a grayish metal. So we're going to look at the specific heat table, scroll down to silver, and see that its specific heat is 234 joules per kilogram degree Celsius. Because every different material has a different specific heat, you will not be expected to remember any of them. You will have access to a table like this on your formula sheet, or the question will give you every other piece of information and then you solve for specific heat. So we're going to assume that we have 100 grams of silver. That silver began at an initial temperature of 25 degrees Celsius, and the metallurgist is going to heat it up to a final temperature of 800 Kelvin. So the question is, how much thermal energy does this feat take? How much thermal energy needs to be added to something to make this happen? So let's look at our formula. We want thermal energy. We want Q. So Q is equal to our mass, which is 100 grams. All of our formulas take kilograms, so we need to go ahead and convert that. 100 grams is going to be 0.1 kilograms times the specific heat of silver, that's 234, times our change in temperature. Delta anything is always final minus initial. Our final is 800 Kelvin. Our initial is 25 Celsius. So, are we good to go? Trick question, we're not. We already converted grams to kilograms, which is good, but the issue here is our temperature units don't match.
So we have to convert Celsius to Kelvins and then subtract?
Yes. This formula specifically, you can put either Kelvin or Celsius in for delta T, but you can't put in both at the same time. Whatever your two temperatures are here for delta T, they have to be the same unit because you can't just subtract Celsius directly from Kelvin. So we need to convert one of them first. And I am going to put up on the board converting the Celsius temperature into Kelvin. This marker is dying as well. Temperature Kelvin is equal to temperature Celsius plus 273. So our Kelvin temperature is going to be 25 plus 273, which is 298 Kelvin. So we're going to plug 298 Kelvin up here instead of 25. As a rule of thumb, general rule of thumb, 25 degrees Celsius is room temperature. So most dwellings keep their internal temperature at about 70-ish, 70 to 75 degrees Fahrenheit. That 70 to 75 degrees Fahrenheit correlates to about 25 degrees Celsius. So that was already room temperature in Celsius. This is room temperature in Kelvin. It's the same temperature. Just want to get into your head as a frame of reference. The temperature that you are experiencing right now is probably around 300 Kelvin. That's normal. It's just to get the sense of scale in your head. So we've converted the Celsius to Kelvin. Again, you can put either Celsius or Kelvin in for delta T here because 1 Kelvin is equal in size to 1 Celsius. The units will work fine if you use Celsius or Kelvin here, but you cannot use both at the same time. Your TF and your T initial have to have the same unit, otherwise they won't subtract correctly. Now that we know that, we know every variable in the equation, so we can solve for our heat. As I fish my calculator out of my backpack. And we should get a final answer 11,746.8 joules. Which is not a terribly small amount. That's a decent amount of thermal energy. But keep in mind, silver has a very low specific heat, and this is not a lot of silver. So, relatively speaking, this is not a whole lot of heat. It would take more heat to make water boil. It would take more heat to make water boil. As another sense of scale, we'd get the same answer if we converted both of these temperatures to Celsius first. And again, you get the same answer if you used Celsius instead of Kelvin. The initial temperature would be 25, and the final temperature would be 527 Celsius, which is a lot. That's much, much hotter than when water will boil. So this amount of thermal energy was able to radically increase the temperature of this silver. But if we were looking at any quantity of water, it would take way more energy. This is not enough energy to make water boil. To prove that fact, actually, I'm actually going to work a real quick extra example with you guys. Does anyone have any questions about getting to this number? Okay. Real quick, I'm just going to plug in some numbers related to water just for a quick proof of concept. The specific heat of water is 4,186. And let's just see how much thermal energy it would take to increase water's temperature from room temperature to the temperature where it boils. That's 100 Celsius. So let's say it's the same mass of water even. 100 grams of water. So the same mass of water would take about 3 times as much thermal energy just to get from room temperature up to boiling. So just to help put these numbers into perspective. Any questions about this formula or how we've used it so far? You can ask either over the microphone or via the chat function. Okay. Now there is a specific case I want to show you before we move on about this particular formula. I would like to remind you about the law of conservation of energy. Energy cannot be created or destroyed. So let's say that, as we're heating up the silver or the water, we're adding thermal energy to that object. That has to come from somewhere. Some object has to be losing thermal energy if some other object is gaining it. And energy can't be destroyed. That means that thermal energy already existed somewhere else. So, as a general rule, the thermal energy gained by one object will be equal to the thermal energy lost by another object. The energy cannot be created or destroyed. It has to come from somewhere, and whatever object it came from lost the same amount as the other object gained. There is a negative sign here. That is on purpose, because Q gained is going to be positive. You gained a positive amount of thermal energy while your temperature increased. Q lost is going to be a negative number because the object's temperature that lost thermal energy went down, so it's going to lose thermal energy. This negative sign here is to equalize that negative out so that you have a positive on this side equal to a positive on this side. So that negative is there for a reason. Q gained equals negative Q lost. So, brief reminder of the law of conservation of energy. We're now going to talk about, we're going to close this particular chapter 7, talking about phase change. We've talked about the phases of matter, the states of matter, solid, liquid, and gas. And I want you to turn to slide 19. Dang it. And on slide 19 is a very specific graph that we're going to talk about. There's a graph on this slide that I'm going to draw up on the board so that I can point to it and color things in. This is a thermal energy versus temperature graph. The x-axis is going to represent thermal energy added to an object. So as we scale horizontally across the graph to the right, it's gonna show what happens when you add more and more thermal energy to something. On the vertical axis is temperature. So, in general, when you increase thermal energy in an object, the object's temperature is going to rise, right? You add energy to something, it's going to get warmer. So, it would be reasonable to assume that such a graph would probably look something like this. A line representing the fact that as thermal energy levels rise, temperature will also rise. This would be a reasonable assumption to make. And as you increase temperature, an object's phase, its state of matter, is going to change. So along this sort of a hypothetical graph, we would go from solid to liquid to gas as the temperature rises. But when you actually examine, like say, an amount of water, as you add thermal energy to it and its temperature rises, if you're monitoring its temperature the entire time, the graph does not end up looking like this. It looks more like the slide on screen right now. So we're going to step through that particular image, one little chunk at a time. The graph is going to begin at the origin. This origin point here represents absolute zero. This is the point where thermal energy is at an absolute minimum, where an object has no thermal energy. And on the temperature scale, this represents a temperature of, well, the temperature you'd be at when you have no thermal energy, and that's absolute zero. So that's what this origin point here is. Now, at that origin, as you begin warming up, the object is going to be in solid state, because that is the phase that that most objects are in when they are at their coldest. So Let's say that this is a block of ice. This is some mass of ice. And as you increase the ice's temperature, as you increase the thermal energy level of the ice's temperature is going to rise. It's not melting yet. It is still ice. We have not hit the temperature where it would begin to melt yet. We're just going from absolute zero ice up to 0 Celsius ice. As you do this, its temperature is going to rise. Eventually, you will hit a specific temperature. Eventually, you will increase the temperature to the point where the ice will begin to melt. For water, we know that's to be 0 Celsius, 32 Fahrenheit, 273 Kelvin. Once you hit this temperature, something weird starts to happen. You add thermal energy to the ice, and it starts melting. But first of all, does the entire block of ice immediately turn into water? No. If you take some ice out of the freezer and put it outside, just because it's now exposed to a higher temperature, it does not immediately liquefy. It is a slow process where water starts dripping off of it one bit at a time. Additionally, if you have a water bottle with ice in it, there is both water and ice together in this vessel. The ice is at 0 Celsius. 0 Celsius is the warmest temperature that ice can exist at. You can take ice out of the freezer. The ice will be sitting in a room that is warmer than 0 Celsius, but the ice itself has a maximum temperature of 0 Celsius. Ice can't be warmer than that. Its own innate temperature can't be. But notice, in the same vessel, there is also water. The ice and the water are touching one another. They're trying to be in thermal equilibrium. So in this container right now, there is 0 degrees Celsius ice and 0 degrees Celsius water. And the water isn't immediately freezing. The ice continues to exist at this temperature, and the water can continue to exist at this temperature. The melting point is not the temperature where the phase change magically immediately happens. It's the point where the phase change starts, and it's the temperature where both the solid and liquid form of an object can exist at the same time. 0 Celsius is the highest temperature you can have ice, the lowest temperature you can have water, and they can both exist at the same time at that temperature. Once you get the ice to this point, it's still ice. In order to make it melt, you have to keep adding thermal energy to it. The more thermal energy you add to a block of ice, the more it will slowly melt, eventually until you've added enough thermal energy such that all of the ice melts. But as you're doing that, the ice's temperature is not increasing. Ice has a maximum temperature of 0 Celsius. The ice can't exist at a higher temperature. So you're still adding thermal energy, but the ice has not changed its temperature. This is one reason why cooling your drinks with ice works. It will get the drink down to 0 Celsius, and it will stay that way until all of the ice is gone. You keep adding thermal energy until all of the ice has melted. Only once all of the ice has melted, then if you keep adding thermal energy, then its temperature will resume rising. But at that point, you don't have ice anymore. Now you have the liquid state. So, to cause a phase change, you have to get the material to the temperature where the phase change will start, and then you have to keep changing the thermal energy level to make the phase change happen as it stays at the same temperature. Solid ice stays at 0 Celsius while it is melting until it is done melting. Again, if it didn't do this, it would be very bad at cooling your drink. Once the ice is melted into water, and once it's entirely water, if you keep adding thermal energy, the temperature will keep rising until eventually you hit the water's boiling point. So that's going to be this temperature here. This is the boiling point. And this is the temperature where the water will start to boil and start turning into steam. Liquid to gas is another phase change. And when you're boiling water to make noodles, once the water starts boiling, it does not immediately turn entirely into steam. The water remains water and boiling at 100 Celsius until all the water has evaporated. The water in the pot remains at 100 Celsius until all of the water has become steam. So as you keep adding thermal energy, it stays at 100 degrees Celsius until the phase change is done. Once the phase change is done and all of the water has turned into steam, then if you keep adding thermal energy to the steam, it will keep getting warmer. And this is the reason why we can cook food in boiling water. Boiling water is just a very good way to keep something constantly at 100 Celsius because the water won't get any hotter than that until it's done evaporating. So the main thing I want you to take away from this, the main factoid is phase changes happen at constant temperature. Temperature of an object won't change until the entire phase change is done. This is true of going up the chain. It's also true going back down the chain. If you're going from gas to liquid, you have to get the gas down to this temperature, remove enough thermal energy from it to make it liquid, and then its temperature will go down as you remove more thermal energy. Phase changes happen at constant temperature. Another thing that's worth knowing is actually the fact that because of this rule, all steam is always going to have more thermal energy than all water. Steam has more thermal energy in it than water, and that's why steam burns are especially nasty. So be careful in the kitchen in general. Steam burns are not fun. So that is some of the principles behind phase change. And these phase changes are caused by an object possessing more thermal energy. If you recall, the more thermal energy an object has, the more its particles are jumping and bouncing around. They space naturally farther apart. As they're spacing apart, that is sort of how the phase change happens. You warm up a solid, its particles begin spacing out until eventually they're so far apart they can't maintain solid shape and they turn into liquid. The liquid particles keep getting farther apart as you increase the temperature, the thermal energy level, until eventually they're so far apart they break free of one another and become a gas. So, we've talked about phases, but that's just some of the science as to how phase changes occur and some details about how they occur. Any questions about this, any of this information before we close for today? Okay. Okay. Before we go, there is one more slide, slide 20, and it has some vocabulary words for you. These are just some concepts, and the terms at the bottom are useful to know. We've been talking about the process of objects either gaining thermal energy or losing thermal energy. And there are more scientific terms for those. Those terms being endothermic and exothermic. An endothermic process is a process where an object is absorbing heat from its surroundings. So if an object gains heat, it is undergoing an endothermic process. Thermic means of or referring to temperature. Endo means inward. So inward thermic means absorbing thermal energy. That technically means that melting and boiling, the two processes where you add thermal energy to H2O, are endothermic processes, which means they have the effect of cooling the world around them. Technically, if you boil something, you are making the surroundings colder because the water is absorbing thermal energy that was in its surroundings. So the surroundings now have less thermal energy and the water has more. So endothermic processes like melting and condensate, like melting and condensation. Oh, I misspoke. Melting and condensing. No, sorry, what? I'm confusing myself all over the place. I apologize. Let me start from the beginning. Melting and boiling are cooling endothermic processes because they take thermal energy away from their surroundings. This is one reason why human sweat cools us down. The sweat exits your body and then evaporates. When it evaporates, it takes thermal energy away from you in order to turn into steam. So sweat is gross, but it does serve a practical application. The opposite of endothermic is exothermic. The word exo means outward. So an exothermic process is giving heat away to its surroundings, which means that exothermic processes warm up their surroundings. Technically, this includes freezing and condensation. Condensation is the name for a phase change when a gas turns into a liquid. When you freeze something, it is giving up thermal energy in order to get colder. So when you freeze one object, its surroundings get warmer because it has now vented its thermal energy into its surroundings. So freezing and condensing are technically exothermic processes. Exothermic processes give heat away from the object in question and gives it to its surroundings. These vocabulary terms will be important next week because we're going to be talking about how thermal energy can make a system expand and contract and how that happens based on whether the process is endothermic or exothermic. So that is the end of the Chapter 7 material. That's everything you need to do your Chapter 7 assignments. The homework, quiz, and lab are due for Tuesday. So next Tuesday, we will resume our normal meetings, and you'll have time to ask any questions you have about the Chapter 7 assignments before they are due that night. Next week, resuming as normal means we will have normal labs again. There will still be online options for those who can't or are unwilling to, or for those who cannot come in person. But we've reached the end of the period. You can stick around if you have any questions, but if you do not have any questions, I do hope you have a wonderful day and a wonderful weekend. Anyone have anything before you head out? Okay. We don't have, there's no lab period on Friday, so we don't have office hours today. So this is the last of the video call time for today. But if you have any questions about anything at any time as you're working over the weekend, you can email me, we'll communicate. Just let me know. You can work on the homework and the labs with each other in groups over the weekend. I'm rambling at this point. Have a great weekend, guys, and hope to see you back here pretty soon. Stay safe. Stay healthy.